So, we were discussing about this producer consumer problem. So, in case of producer consumer problem, what happens is that this is a very standard problem that we have in operating system. So, there are some process which are producing some data and there are some process which are which is actually consuming that data. An example of it that we have told in the last class, like there may be I have a program written that finds roots of a quadratic equation. So, that program, so that is so it is doing like a x square plus, it is finding roots for the equation a x square plus b x plus c. Now, this program, so it needs to read the values of a, b and c from the user and then it will proceed finding the roots. Now, this reading process of this a, b, c, so they are from either from say keyboard or they may come from some file etcetera. They may come from some file etcetera. So, whatever it is, so there is an input process. So, I can say that there is an input process from where the data is coming and then this input process is there. So, it is in communication with the program that is actually doing this computation. So, this root computation program that is there. So, it is actually they are in communication with each other. Now, if this input process is slow, which is often the case when human beings are involved. So, then if this root computation process it reads something from the this a, b, c. So, they are in some shared memory location, as you can understand, because they are shared between the input process and this root computation module. Now, if this a, b, c, if the root computation module is very fast, then of course, it will not get the proper values of a, b and c. On the other hand, if this if there is a continuous flow of roots. So, if I just modify the statement of the program that it gets a series of values of a, b and c and for each of them it computes this value the roots. Okay. So, if we say that it will go like that, then there may be a case that this data set is coming at a much faster rate than the rate at which those roots can be computed, the corresponding roots can be computed by the root finding routine. Now, that type of situation how to handle. Okay. So, there basically what I want to mean is that there is a speed mismatch between the input process and the computation process, or in terms of this the producer process. So, the input process, that is the producer process, and we have got this consumer process. So, that is the root finding process. So, if there is a speed mismatch between this producer process and consumer process, then how to handle this situation. So, that if we want to handle, then we can put a buffer in between, we can put between the producer process and consumer process a buffer, and so that if the producer process is fast, then it will be writing onto that buffer and the consumer will be consuming from this buffer. So, some part of the speed mismatch will be taken care of. And again, this buffer can be of two types. One possibility is that buffer is unbounded in size. So, there is no practical limit on the size of the buffer. So, though it appears to be impossible, but for all practical purposes, so we can put a sufficiently large buffer, so that this producer will never be able to fill up this buffer if the consumer is also running. Other possibility is that which is more realistic in nature, the buffer size is bounded. So, that is a bounded buffer situation. The buffer size is has got a fixed size. So, in that case, when the data is produced by the producer, after some time producer has to be made to wait, so that the consumer consumes some of the buffer content, and then only the producer will be able to proceed again. So, we will see that there are two variants of this problem, and each of them gives rise to different levels of synchronization problems. So, if I say that for the bounded buffer problem, so if we have to define some buffer size, and this item, so we have to whatever be the content of this buffer type. Okay. So, that is not written here. So, it can be depending on the application that we have. So, there can be different types of items in the buffer. So, then we can, so we are defining the type def item, and then item buffer. So, this buffer is of size buffer size, then there is input pointer and output pointer, input index and output index. the solution presented here is correct, but only 9 out of 10 buffer elements can be used. So, let us see how is it done. So, bounded buffer producer. So, the producer problem. So, what it does is that the process is an infinite loop. So, while true, so this is an infinite loop. So, it produces an item in the next produced this variable. So, next produced is a variable of type item. So, the item is produced in next variable. So, while in plus 1% buffer size not equal to out. So, do nothing. So, basically is equal to buffer. So, I have got a buffer, sorry. So, I have got a buffer and initially this input and output. So, both of them there. So, this input and output both the indices. So, they are made equal to 0. So, this is the buffer. So, the input pointer and output pointer. So, both are equal to 0. This is the location 0. Now, so in plus 1%, so buffer is empty. So, in plus 1% buffer size. So, in plus 1 is 1%, buffer size is not equal to out. So, it will not be here. So, it will be executing this statement buffer in equal to next produce. So, at location in, so location 0, it will produce an item and write it here. Then this in pointer will advance, in will come to be equal to 1. So, this way assuming that the consumer is not there. So, this buffer will be filled up one by one and this in pointer will come to this last space buffer this value of 9 and then it will go back to in equal to 0. So, it will go back to there. Now, that is how this producer process runs, and only thing is that, so after, so maybe this consumer process is present, but the consumer is a bit slow. So, after this producer has produced say up to this much of items. So, consumer came and consumer consumed something. So, this consumer pointer will come to the next place. Okay. So, it will come to the next place. So, that when this producer comes back, it finds that some part of the buffer is already consumed. So, in this part, so it can continue writing a here. But it may so happen if the consumer is slow, but producer is fast, then it is at a situation where this producer, so consumer is currently at this point. So, it will next consume this item, and producer is at this point, the input pointer is somewhere here. So, it is trying to write on the next location after this. So, at that point this while loop will make it to wait, while in plus 1% buffer size is equal to out. So, in that case the producer is made to wait. So, that is how this buffer, if the buffer is full, then the producer is made to wait till the consumer has consumed something. So, the reverse thing should happen about the consumer, because consumer should not consume from an empty buffer. So, how that is done? So, that routine is here next consumed. So, if in equal to out, so in and out they are same, that means the whatever the producer was going to produce. So, it will write onto that slot at which the consumer is also pointing to. So, if this is the buffer, so if in equal to out means, so it is somewhere here. Okay. So, in is here. So, the producer will write will try to write onto this location, and the consumer is also here. So, so that means consumer here means consumer has consumed up to this, and next it will try to consume the next one. But there is nothing in the buffer, because this in and out both of them are same. So, as a result the consumer should be made to wait. So, if while in and out are same, then the consumer is made to wait, otherwise the consumer is made to consume from the out location, and then the out pointer is incremented to out plus 1% buffer size, then it will consume it and produce. So, this way we can have a synchronization between this producer and consumer, and with respect to the buffer size. If the buffer becomes full, then the producer is made to wait. If the buffer becomes empty, then the consumer is made to wait. So, this way this producer consumer this bounded buffer version can work. Of course, there are other issues like say this input output modifications when being done. So, we have not ensured that producer process is not reading from the buffer when consumer is also trying to producer process is not writing onto the buffer when consumer is also reading from the buffer, or vice versa. Because it may so happen that the producer and consumer, they are trying to access this buffer space simultaneously, as a result there is some synchronization mismatch, but this type of problems we will see later in the course. So, right now we just keep ourselves satisfied with the idea that we can synchronize between producer and consumer and try to do something to take care of their speed mismatch. So, then another type of situation that we can have is the message passing case. So, message passing systems, so they have got, so they are for processes to communicate and to synchronize their actions without resorting to shared variables. So, there is no shared variable. So, the processes, if they want to communicate, they will send explicit messages to the from the sender to the receiver, and this there are two system calls send and receive. By means of these messages can be sent and received. Okay. So, sender process will execute will use send system call, and the receiving process will execute receive system call. Message size can be fixed or variable. So, depending upon the operating system, some operating systems will allow you to have variable sized messages, some operating systems will have only fixed size messages. So, you can have different message sizes. So, this is there. So, these message passing systems are also there in different operating systems. So, if processes P and Q wish to communicate, they need to establish a communication link between them. So, this is the first thing. So, I have got two processes P1 and P2. So, that P and Q. So, between them I must establish a communication link between them, so that this process P can write onto this Q into this link, and process Q can read it. Similarly, process Q can write here and process P can read from here. So, that is exchange messages via send or receive. So, process P can send messages, process Q can receive messages, or vice versa. Now, the questions that we need to answer is how are these links established, that is the first thing. Second thing is that can a link be associated with more than two processes? Can I have a message queue that covers more than two processes? Then how many links can there be between every pair of communicating processes? So, is there a single queue or there are multiple queues? So, there is another queue like that. Okay. So, many things to be answered, or maybe the same message queue, it feeds not only queue, but also another process Q1. So, can it be there? What is the capacity, like how many messages can I send, or how big messages can I send through this queue, that is also through this link. So, that is also another thing. Is the size of a message the link can accommodate fixed or variable? So, message size, so message format, can it be of fixed length, or is it needed that they should be of fixed length, or can I accommodate variable length also? Is the link unidirectional or bidirectional? Unidirectional means that whether it always goes from P to Q only, or it can also come from Q to P. So, these are different alternatives that we can think about a communication link between two processes or multiple number of processes, and many operating systems they will try to answer these questions in different ways. Okay. So, each of them have as you are making the system more and more complex, and you are trying to accommodate more and more flexibilities into the message queue, then into this message passing mechanism. So, this implementation will become more and more complex, but this depending upon the flexibility that we need. So, we may like to do many things. So, there are as far as the implementation is concerned, so we can have physical communication. So, physical communication, the communication link. So, there should be a physical part and there should be a logical part, because physical means the communication may be via shared memory. So, just like we have discussed about this shared memory creation, like that SHM gate system call and all that. So, similarly, we can have some dedicated part of shared memory which acts as message queue between two processes. So, that is one possibility. So, we can have one physical communication like that. There can be hardware bus. So, maybe I have got multiple processors. So, they are connected to a bus, now over the bus the data transfer takes place. So, that is one possibility. So, over hardware bus we do this physical communication, or over a network we do the communication. So, they are the processors, they are distributed over a network, and over the network we send messages, receive messages, like that. So, we can have this type of physical platform over which this communication link can be established. And logically there can be different classification, like whether the link is direct link or indirect link, whether it goes via some other nodes or things like that, or it is a direct point to point sort of link. Then synchronous or asynchronous. So, is there any global clock that synchronizes this operation of this transmitter and receiver, and so that is another thing. Automatic or explicit buffering. So, buffering that we need, maybe if the message is long or multiple messages are being sent without waiting for this receiver to receive it. So, are you doing it using some buffering or not? So, that way again different questions need to be answered, different mechanisms can be there. So, as far as direct communication is concerned, so processes must name each other explicitly, like there are send and receive, these two system calls that are used for sending messages. So, this call like send p comma message. So, this essentially means that I want to send a message to the process p. So, send a message to process p. Similarly, receive q message. So, receive a message from process q. So, that way we can have explicitly we can mention to which process we want to send the message. So, it may so happen that between, so p, this is p and this is q. So, p has got q, it wants to send some message to q, and also it wants to send some other message to process p 1. So, another message to process p 2. So, it has got communication with many of them, but it wants to send this particular message to q only. So, it can use like send q comma message 1, where message 1 is a data memory structure, some variable structure in the form that is put into the form of message, and then this message is sent to q. So, when it wants to send to p 2, so it will write like send p 2 comma some message m 2. So, it may like to do that. So, we have got this send system call. Similarly, this receiving end, so it can tell from which source it is expecting the message. So, that is from the receive statement example that we have here. So, it is expecting that it will get a message from process q. Now, these properties of communication links that we have. So, communication links are established automatically. A link is also associated with exactly one pair of communicating processes. So, between every pair of communicating process we have got one link. Between each pair there exists only exactly one link. So, and the link may be unidirectional, but it is usually bidirectional. So, these are some of the properties of communication link that is generally followed. So, we have got different type of different parameter or different properties of them. They are generally they are whenever a message is being sent, the link is automatically established. So, it is between one pair of communicating process. So, each pair exactly one link, and the link is bidirectional in nature. In case of indirect communication, so messages are directed and received from mailboxes, also referred to as ports. So, each mailbox will have a unique ID, and processes can communicate only if they share a mailbox. So, every process has got an associated mailbox. So, anybody wanting to send a message to a process, so it will send a message to the corresponding mailbox, and the receiving process, so it will just read it from the mailbox instead of telling from which receiver it is expecting a message. So, it will just read it from the mailbox and find out from which receiver, which transmitter the message has arrived. And of course, there should be permission. So, for this mailbox sharing and all, so that is there, but once the permission is established, so it is done like that. So, operations that we have, so create a new mailbox or port, send or receive messages through mailbox and delete a mailbox. So, these are some of the operations that is there. So, for example, primitives we have got send a comma message. So, it is sending a message to mailbox A, receive a comma message, receive a message from mailbox A. So, we can have this type of things. So, they are all associated with some mailbox. So, if two processes they share some mailbox, then mails sent to one mailbox by one process will be visible to the other one also. So, this is indirect way of communication, because we are not telling directly to which process we are wishing to send the message, but we are mentioning a mailbox only. Similarly, at the receiving end we are not telling from which process we will be receiving we want to receive the next message, but we are just telling that what is the next message that we have in the mailbox, and accordingly take some action for doing that, handling it. Then properties of this communication link. So, link established only if processes share a common mailbox. A link may be associated with many processes. Each pair of processes may share several communication links, and link may be unidirectional or bidirectional. So, these are the properties of communication link in case of indirect communication. Some other issues like mailbox sharing. So, P1, P2, suppose this is the situation, P1, P2 and P3 they share mailbox A, P1 sends and P2 and P3 receives. Now, who gets the message, like for whom P1 did send it, and since they are sharing the mailbox, so we do not assume that they are there is a leaking of information from for them. We assume that anything that is sent should be even if it is seen by some other process between this P1, P2 and P3. So, it is not hampering the security issue, but the point is like who should read this who should read the next message. So, what can be the solution? Solution is to allow a link to be associated with at most two processes. So, if I have got mailbox, a single mailbox A in this case was associated with three processes P1, P2, P3. Instead of that, we can create two mailboxes, one between P1 and P2 and one between P1 and P3. So, that way we do not have this type of problem. Okay. So, we do not have this which process gets the message. So, that problem will not occur, or we can allow only one process at a time to execute a receive operation. So, somehow we ensure that two processes will not execute this receive simultaneously. So, how do we do this? So, that is another issue. So, operating system should ensure that only one process will be executing the receive operation. So, otherwise what will happen is that maybe we have sent this P1, it has sent some message. So, P1 has sent some message, okay. And so this I have got P2 and P3. So, this P2, P3 these processes are there. Now, P1 has sent a message to the mailbox. So, in the mailbox some message has come. Now, both P2 and P3 tries to access it, and as a result, so there may be some inconsistent situation that can occur, because maybe P2 has read it half and then P3 is trying to read, or maybe P2 is reading has read it and it has deleted the message from here, but P3 was also reading it from here. So, that way there may be several inconsistencies that can come. So, we have to somehow ensure that only one process will execute the receive operation at a time. So, operating system must ensure that receive is done by only a single process, or we can allow the system to select arbitrarily the receiver. So, and then the sender is notified who the receiver was. It may so happen that the system decides like who gets the message. So, if P2, P3 both of them issue a receive call, then maybe it will take up one of them, maybe P2, and then the operating system will inform P1 that your message was picked up by process P2. So, this is one possibility, that arbitrarily the receiver is selected and the sender is notified about the receiver. So, there is another important concept with respect to this messages, blocking and non-blocking scheme. So, blocking scheme is considered to be synchronous. So, basically what can happen is that suppose we have got this process P1 So, which is executing a piece of code. So, this is for P1 and P1 sends a message to another process P2. Now, since it has sent the message, so the message contains some data or information with which P2 will proceed, and when P2 has finished using that data, it should tell P1 that I have done with my operation. So, this is one type of situation that P1 waits until and unless the message has been the message is received by the receiver. So, this is called blocking type of send. So, blocking send, the sender is blocked until the message is received by the receiver, and there is a blocking receive. So, this blocking receive is the receiver is blocked until a message is available. So, maybe P2 was executing. So, at this point it was expecting a message, but this P1 did not send anything so far. Okay. P1 has not yet sent it, maybe P1 is slow or it was not scheduled, etc. So, at this point when P2 executes a receive call, so P2 is made to wait. So, P2 is made to wait that since no messages are available, so it is made to wait. So, we have got this blocking send and blocking receive. So, blocking send is something like this, the message is sent, but there is no receiver, message is not received. So, that is the blocking send, and blocking receive is that receiver is blocked until some message is available for receiving. So, this is one type of mechanism. So, this is called synchronous because we have got synchronism between the sender and receiver of messages. There is another type of situation which is known as non-blocking or asynchronous situation. The non-blocking send, the sender sends the message and continue, and so what happens is that here in this case P1 it at some point it sends the message, but without waiting to see that whether the message is received by the receiver or not. So, it will continue doing the next operation. So, eventually the receiver will receive it and do the corresponding operation. So, the sender sends the message and continue, and other case is the non-blocking receive, and the receiver receives a valid message or a null message. Like if the P2 is the receiver and at some point it executes a receive call. So, it executes a receive call. Now, it may so happen that at this point some message is available. So, it gets the message, or if P1 is slow, then it will not get any message. So, it will get a null message. So, whether the valid message or null message, with that the receiver will continue, but receiver will not wait for the message to be available. So, it executes a receive. It is good if it gets a valid message, otherwise it gets a null message, but whatever be the situation, it continues with the further statements in the program. So, we can have different combinations of possibly both sender and receiver are blocking. So, we have got this rendezvous type of situation. So, that way we can, so different operating systems, so again they will implement different combinations of this message passing, blocking or non-blocking, and you have to consult the corresponding operating system manual to see what type of message passing is supported by that.